I apologize for the slight delay. Somehow I thought it was starting at 11:55. Let me just see. Okay. Okay. So welcome everyone. Let's get it started. So today's recitations are on combinatorics. And we'll review some basics from the lectures, and then we solve a bunch of problems. We'll do some breakout rooms. We'll try to solve them together. That's the way you learn this material. Okay. If you have any questions, feel free to ask them in the chat or just unmute yourself and ask the question. That's fine too. So let's start with a couple of announcements. We're almost done grading quiz 3. We will post the grades probably by tonight. If not, then tomorrow the latest. And then I also want to mention TAs brought up some concerns about the length of quiz 3 to us, because you mentioned those during the discussion sections last week. And so we'll discuss these. And having said that, quizzes 4 and 5, just by the nature of the material, are a little bit easier. So you can expect the next quiz to be a bit easier. We will try to grade homework 4 by the end of this week. There is a lot of grading. We're doing our best. So hopefully by the end of this week, it'll be graded. We released homework 5, so you can take a look at it. You can start working on it. Don't forget about that. And then finally, all of you are probably aware of this. Elections are happening next week on November 3rd. And because of that, as per college guidelines, there will be no synchronous recitations that Tuesday. So you don't have to join in this preset time. However, we will post a recorded recitation for you to watch. And then on top of that, there will be no office hours, again, as per college guidelines, on Tuesday and Wednesday next week. Except that I will hold mine on Wednesday morning. So we didn't want to force TAs to hold office hours, but I'm okay doing it. So Wednesday morning next week, you can come to my recitations. If you have any problems related to the 100 that you want to discuss, or if you want to chat about the elections, I guess. And we're doing all of this so that you guys can go and vote. If you still haven't done this and you haven't registered online, you can still register in person. So there is plenty of time to register and go and vote. So these are my announcements. Any questions about the announcements? Okay, great. So let's review some basic rules and structures that we used for counting. We did go over all of this in the lectures, but it doesn't hurt to quickly remind you. So we covered a couple of different rules. We have rule of products. So if we can select values individually, then we can multiply counts if we want to combine them. And in the problems that we'll be solving today, we'll use rule of products and rule of sums and rule of complements. So rule of sums tells us that if you can split the problem into disjoint sets, then you can add the counts to get the final count. The special case, this is if the sets are disjoint. That's important. The special case of rule of sums, for the case when the sets are not disjoint, tells us that we must subtract the count of the overlap from the total count. Rule of complements, if we want to count the object of certain property, we can count the opposite and then subtract from the universe. And then we covered different types of structures. We covered order lists, permutations, bags, and combinations. And we derived formulas for counting all of these. How do we distinguish between the structures and how do we decide which one to use? It's based on whether we have repetitions, whether repetitions are allowed, and whether the order matters. So those are the two questions that you should ask yourself first when you're looking at the problem. And based on your answer on those two questions, you decide which structure to use to solve the problem. So here's how we derive combinations. And then binary sequences of bags. We also derive the formula. We also showed that it works on a bunch of different problems that are all equivalent. The main one is this last one related to counting the number of bags of R items with n item types. Okay, so that's a quick refresher. You should already be familiar with all of these from the lectures. Any questions so far? Okay, so let's then go and solve our first practice problem. So what does the problem say? We have 3 members of a 20-person office that are carpooling. And so these members insist on never working separately because they want to carpool together. That means that whenever one of them is on a committee, all 3 must be on this committee. And now, if that's the case, the question is how many 7-person committees can be formed? So I'll give you a couple minutes to first work on this on your own. We're not going to do breakout rooms now. We're going to do breakout rooms for the next problem. But still, I'll give you 3 minutes. Try to solve this on your own. One thing to note here, so we don't distinguish between members of the committee, which means that the order does not matter. And also repetitions are not allowed. Clearly, we cannot put the same person twice on the committee. So that tells us which structure to use. And then we'll have to play with 2 cases here. So one case is when these 3 members are not on the committee, and the other case is when they are. So that gives us the structure of the solution. Okay, I'll give you now 2 minutes. Try to solve it on your own, and then I'll do it, and then I'll answer any questions you might have. Okay. So let's go ahead and let's solve this. So like I said, we have two cases. Whoops. Wow. Not sure what happened here. Huh. Can you guys see this red line? Okay, okay. It disappeared now. That was weird. I don't know what happened there. I hope you didn't see it, or maybe you did. I don't know. Sorry about this. Okay, so let's solve this. So we have two cases, like I said. So case one. So carpooling. Not on committee. And then we have case two, which is carpooling on committee. Okay, and the final count, all elements of the final count belong either to case one or to case two. So we will use the rule of sums to add the solution for these two cases up. So let's solve the case number one. So the carpooling people are not on the committee. So that means that we are choosing 7 people to fill the whole committee out of 70 leftover people. Why 70 and not 20? Well, because we know that the 3 carpooling people cannot be on the committee. So we cannot choose from them. There's a solution for case one. Solution for case two. Carpooling people are on the committee. So that means that we chose these 3 people and we place them on the committee. So now we have 4 leftover spaces on the committee, and we want to fill these 4 slots on the committee from, again, 70 people, because we already placed the 3 carpooling one on the committee. So that's the solution for case 2. And now we have to apply the rule of sums. And so the final solution is going to be choose 7 out of 17 plus choose 4 out of 17. So that's the final solution. One quick note here. So I'm not going to compute the actual final number. And in the quiz, we are going to specifically tell you whether we are looking for the actual final number or whether you can leave it in this form. And that will depend on how large the number is. Sometimes the number is fairly small, or whatever, under 100. Then we'll ask you to actually compute it. And I'll show you that on some of the practice problems. When the number is bigger, you can leave it in this form. Okay, any questions about this one? Feel free to speak up or write it in chat. Okay, there is a question for case 2. Yes, please feel free to speak up or write it down.
I have a question.
Yes.
How do we know that we're adding the 2 rather than multiplying them?
Great question. The same question came up last time, and I speak it in the last recitations. So I think it will come up in all recitations. So the way I like to think about this is whether the cases are connected using an or using an and. And we'll see an example. So if they're connected using an or, then you have to add them up. So in this case, the committee is either a committee without these people, or it is a committee with carpooling people. So it's either or. In that case, you're using rule of sums. And we'll see an example where you have the end between these two. And in that case, you use product. Another way to think about this, this is maybe a little bit longer explanation. So these two cases, right, they consist of completed committees, right? In the first case, we are counting completed committees where carpooling are not on a committee. And in the second case, complete committees of 7 members when carpooling guys are on the committee. So in that case, you use rule of sums. So because your final solution belongs to one of these two sets. Rule of products, as we'll see, we use it when we try to assemble, how to say, a complete solution from smaller chunks. So in that case, we will not be able to say, oh, our final solution belongs to one of these chunks because these chunks will be incomplete. And we'll see how that looks like. But this is a good question. I hope this helps. Any other questions? There is a question in the chat. It's a great one. Very illustrative question of a common problem. So the question is, how come we didn't multiply this 17,4? We choose 7,3 because there are choose 7,3 ways to put 3 carpooling people to 7 positions. So that's a great question. So the question is, how come we are not multiplying this with choose 7,3? Because we have to place these 3 people in 7 positions. We're not doing that because the order of people on the committee, as I said initially when I introduced this problem, does not matter. So in which positions we put these 3 carpooling people doesn't matter. We don't distinguish between the committee where we put them, whatever, in the first place. I mean, there is no places on the committee. There is not even the concept of order of the committee. The committee is just a set. And because of that, we should not be doing this. If the order mattered, then we would have to do stuff like this, as we'll see in some of the subsequent problems. Good question. Any other questions? Okay. Maybe there is one more. So we're moving kind of a little bit slowly to the problems that I have. It's okay. I like that you're asking a lot of questions. And so I won't be able to cover all the problems I prepared in every recitation. And so I will kind of mix and match problems a little bit. So I suggest that you do, all the recitations will be available. They're all recorded. So I suggest, maybe tonight you can kind of quickly go through all of them and find in other recitations problems that I won't have time to cover in this recitation. Okay, good. Let's move to the second practice problem I have. And for this one, let's do breakout rooms for maybe 5, 6, 7 minutes. It's a little bit of a longer problem. Try to solve all 4 of these, and then we'll do it together. So a briefcase has an ordered 3-digit lock. Maybe you've seen these briefcases, when you have to kind of usually turn the dials to get the combination. So okay, it already tells us these 3 digits are ordered, so the order does matter. And as a side note, repetitions are allowed. So like 1, 1, 1 is a valid configuration of the lock. The same as 1, 2, 1, and so on. And there is, of course, digits go from 0 to 9. Okay, and now we have a couple of different questions that we want to count. So how many total configurations are there? How many configurations have no repeated digits? How many configurations have the digit 8 appearing exactly twice? How many configurations use the digit 0 at least once? So try to solve all of these. A little hint on the last one. It's a great one to apply the rule of complement because it makes it much easier to derive the solution. So that will be my hint. Okay, let's do breakout rooms now, and then we'll reconvene and we'll do it together. Okay, so please join your room. You can work on it together, discuss the solutions. Yeah. Hey, Lynn, maybe you could join a room as well. And then you can help them out in the room. Thank you. Okay, let's go through these one by one. So first question, that should be an easy one. How many total log configurations are there? Does anybody want to shout an answer?
1,000.
Wonderful, thank you. So 1,000, great. How do we get this? So these are ordered lists. This is an order list, right? Because repetitions are allowed and the order matters. So therefore, we have 10 to the power of 3 configurations because there is 10 digits and there is 3 of them. Okay, any questions? Okay. Second question, how many configurations have no repeated digits? Anybody wants to shout an answer?
We got 10 times 9 times 8 for that one.
Wonderful. Thank you. Thank you, Cole. Yeah, so that's the correct answer. So there are 2 ways to go about solving this. They're both simple. One of them is you can use the rule of products. So we are not repeating digits. So on the first place, we can put 10 digits. On the second place, we can put 9 digits because we cannot repeat the first one. And on the third place, we can put 8. And you multiply this, I think you get 720. Totally fine answer. The other fine answer would be, well, these are permutations because repetition is not allowed. Permutation of 10, 3. And when you calculate this, you get 10 factorial divided by 7 factorial, which is equal to 10 times 9 times 8 is equal to 720. Great. Any questions about this one? Okay, so let's do next one. How many configurations have the digit 8 appearing exactly twice? Anybody wants to shout a number? Just the number, you don't have to tell me the whole thing. Okay, well,
7.
yes?
30 for that?
30, that's one guess.
27.
27, another guess. Any other guesses? Well, let's not call them guesses. You actually computed this. Any other suggestions? Okay. I think some people are writing on chat. Let me try to do this. So, okay. Digit 8 appearing exactly twice. So what is the algorithm we're going to use? In 2 of these 3 slots, let's say we place them here and here. And then we have 1 leftover slot that we have to fill in with 9 leftover digits. We cannot use 8 again because we need exactly 2 8s, right? So that's the algorithm. And let's now see how we would calculate this. So first we are placing these 2 8s. And to place 2 8s, we are choosing 2 slots out of 3 slots total. And after we place 2 8s, we still have to choose the leftover digit, and there is 9 ways to do this. So we use the rule of product here because we are combining these. So we are choosing 2 8s, and then we are choosing this last leftover digit. And then when you calculate this, you get 3 factorial divided by 2 factorial times 1 factorial times 9, and that's equal to 27. So this one is the correct one. So this is coming back to what I was commenting before. Sometimes we'll ask you to compute the actual final numbers. So this is an example of a problem where we'll ask you, okay, write down the process, how you derive the number, and also compute the final number, because it's really easy to do it. Any questions about this one? Okay. Okay, good. So the last one. Here I gave a hint, use the rule of complement. And then computing this becomes pretty easy, I would say. So how do we use the rule of complement here? So the question is, how many configurations we have that use the digit 0 at least once? So using the complement of using digit 0 at least once is using digit 0 times, meaning there is no digit 0. So if we use the rule of complement, you can compute this by total number. That's the thing that we computed in part 1. Minus number of without 0. I'm kind of shortening this. Out 0. Oh no. I think my pen battery is dying. So the total number is 10 to the power of 3. And we have minus. And then the number of configurations that have no 0. So that's going to be 9 to the power of 3, because we remove this one digit. And so that's going to be the final solution. And this is the rule of complement, right? So we have 1000 minus 9 to the power of 3. What do we have? 729. And that is equal to 271. So that's the solution number 4. There was you don't really have to use the rule of complement, right? So you could have calculated this in a more direct way, but it would be a much, much longer and complicated calculation. So you could start, okay, how many of them we have that have digit 0 exactly once? How many we have that have digit 0 exactly twice? And how many we have that have digit 0 3 times? And then you calculate all of these separately, and you use rule of sum to add them up. So that would be another perfectly fine way to derive the solution. However, it would involve many more steps and many more calculations, so it would be more complicated. So any questions about this one? Okay. On the quiz, keep the rule of complement in mind. If you kind of think about how to do it directly and you notice, oh man, this is going to be like a lot of steps, go back to the problem and think about like, oh, can I apply rule of complement here? Maybe it's much easier. So that would be an advice. Okay. Let's do the next one. So what does the problem say? So Charlie and her girlfriend Amber go to lunch at a restaurant with 8 sandwiches on the menu and 3 beverages on the menu. They order 1 sandwich and 1 drink each. And now we want to count in how many ways can they order if they must order different sandwiches, but they can order the same drink. And as a side note, we don't care who orders first, which actually means that the order of the sandwiches and drinks does not matter. So that's the problem. If you have any questions about the problem, please post them in the chat. I'll try to respond to them. And I'll give you maybe 2-3 minutes to work on it on your own. And then we'll solve it together. So give it a try. And then I'll help you out to do it. So think about the rule of sums. You have 2 cases here. You have the order for sandwiches and the order for, that'll be the rule of products. So you have the order for sandwiches and the order for drinks. You can calculate those and multiply them to get the final number. And calculate the final number. It's actually not that large. Okay, so we have 5 minutes left. So let's do this. Okay, so like I said, so we'll do calculate sandwiches. And drinks separately. And because we're assembling these, right, into into the final order. So there is an and between them, right? So we are choosing 2 sandwiches and 2 drinks. So there is an and between them, and therefore this is rule of products. So in the end, we are going to multiply these 2 numbers. So sandwiches is the easier one. So they're ordering 2 sandwiches, and these 2 sandwiches have to be different. And the order does not matter. So there is no repetition because they have to be different, and the order doesn't matter. So these are combinations. So we are choosing these 2 sandwiches out of 8 sandwiches. And that is equal to 8 factorial divided by 2 factorial times 6 factorial. That is equal to, usually this is, you can do this really quickly because lots of things cancel, right? You can cancel 6 factorial against 8 factorial. And the only thing left from 8 factorial is going to be 8 times 7. And then you still have 1 times 2 at the bottom. And you get 28 here. So that's sandwiches. And drinks, the way I did this, there are different ways of doing it. The way I did it is I have 2 cases here. One, they ordered the same drink, in which case there is 3 different ways to do this. And the other one is where they ordered a different drink, in which case now this is the same as sandwiches. We are choosing 2 drinks out of 3, and that is equal to 3. And so we have to add these. So we get 3 plus 3 is equal to 6 different ways for drinks. Because there is or here. So either both of them ordered the same drink, or they ordered a different drink. So in the end, we have 28 different ways to order sandwiches times 6 different ways to order drinks. That is equal to 168. Any questions about this one?
Why is it when they order the same drink, it's just a 3?
Good question. You can even just, you can just count in your head. Either both of them order drink 1, or both of them order drink 2, or both of them order drink 3. So there is just 3 of them. Another way to think about it is you are choosing 1 drink out of 3 drinks. And this 1 drink is the drink that they're both going to order. And that is also equal to 3. Good question. I hope this answered it. Any other questions? So another kind of note for the quiz. And this is what I did in this case, right? If you're counting something where the total count is really tiny, like less than 5 or something, right? It's okay to just count it directly. So this is what I did in this case. Okay. If there are no... Okay, there's a question in the chat. It's a good question to clarify this. So there is no difference if Charlie chooses drink 1, Amber chooses drink 2, or Charlie chooses drink 2 and Amber chooses drink 1. Yes. I was very careful when I was, creating the question and reading it and so on. We have this note in the question, regardless of which one orders first. So both for the sandwiches and for the drinks, the order in which they order does not matter. So you have to be careful. The order doesn't matter. We don't care which one orders first. Any other final questions?
My question was, could we treat the drinks part of the problem with the formula you gave us for finding unordered lists, because order doesn't matter and repetitions are allowed?
Yes, great question. Maybe the second time around the third time around I'll be solving this problem. I'll solve it that way, because I got the same question in the previous recitations. Yes, so good job identifying that the drinks part is basically a bag or an order list. So you are filling up a bag of size 2 with 3 items. So you could have done it that way as well. So great question. Any other questions? Okay, then we'll wrap it up here. Like I said, go quickly through recordings of other recitations, because there'll be probably like 1-2 more problems there. Thank you, everyone. Bye.